the maximum current, I naught. And now, if we go back to our flux calculation and you look at this result right here, wait a minute, V is equal to I naught R. So what's the flux through the capacitor at t equals 0? It's 0. All right? Hopefully that's clear. If not, come see me in office hours. Cheers. Hello class, Professor Anderson here. Let's take a look at a capacitor problem. It's a very simple circuit. We're going to put a capacitor in series with a resistor, hook it up to a battery, and we're going to close the switch and let it charge up. And we want to ask some questions about what's going on inside the capacitor. Namely, what is the electric field flux in the capacitor as a function of time? And what is the current through the circuit as a function of time? Okay, so let's think about broadly what we think that current is going to look like. Well, if we have a circuit and the switch is open, then current is going to be 0 up until we close the switch. So here we are marching along in time. We're at 0 current, and then all of a sudden we turn on the switch, it jumps up to some maximum level, and then we know what happens, it decays. We know that after a very long time it has to go back to 0 because the capacitor charges up and then it stops, right? It can't move current across it anymore because it's two parallel plates. And we know what this curve looks like, right? This curve has a behavior I is equal to I naught e to the minus t over tau, right? This level here is I naught. Tau is, of course, the decay time for this circuit, and that is given by R times C. Okay? Big R means that this thing decays slower. Big capacitor means it decays slower. It takes longer to charge up the capacitor. All right, so this is what the curve for current looks like. So now let's go back to the question. We wanted to figure out what the electric field flux is inside this capacitor, right? What is it through the capacitor? Well, to think about that, we need to do two things. One, we got to understand the circuit here. And if we go back to Kirchhoff's laws says, if I go once around the circuit, all the voltage drops have to add up to 0. Okay? So let's see what we do. If we start at V, we have potential V. When I go through the resistor, I have a drop of IR. When I go through the capacitor, I have a drop of VC. And then I'm back to 0. Okay? I'm back to exactly where I started. So let's just take this equation now and solve it for VC. VC is therefore just V minus IR. Okay, it's whatever voltage you have here minus the current through the resistor. That's what's left over to charge up the capacitor, or I should say that's the voltage across the capacitor. Okay, what about flux? Well, let's go back to our parallel plate capacitor for a second. What does it look like? It looks like two square plates. Okay, so